functions. We're going to talk about their graphs. So we'll start with the most basic rational function that we can have, and that is f of x is equal to 1 over x. And I'm going to graph it with my calculator just so we've got an idea about what it looks like before we even start anything. So I'm just going to go to the y equals menu on my calculator and just type 1 divided by x. This is the most basic of rational functions that we can have. And it looks like that. So I'm going to copy that and put it in my notes there so that I can point to things as we write down some information about this. So I'm going to point out a few things on the graph that relate to what we're talking about. All right. So this one, it has, these lines here, they continue down forever and up forever there, and the same way out and to the left and to the right forever. So those they look like they stop on the calculator, but it's just the resolution of the calculator can't handle it. It kind of cuts off there. So they continue on forever. All right. So every time we talk about functions, we always bring up domain. So that's an important part. So we're going to talk about that. The domain for this function is all x's as long as x does not equal 0. Okay. Or from negative infinity to 0 union from 0 to infinity. The reason it's that is because of this x in the denominator. If we set the denominator, one of the red flags from finding domain was if there's an x in the denominator, we set that bottom part of the fraction equal to 0 and solve it, and that tells you what x can't be. Well, that's where that's coming from. X can't be 0 because we set that denominator equal to 0. When we start adding some stuff to this, it changes that number that's there based on what's in the denominator. We'll see that as we go through some other examples out of that. The range, this is where the graph comes in handy on that. The range is, up and down. Domain's left to right. Range is up and down. So when we talk about the range of this graph, we look at that graph over there, and it goes down. Read it from bottom to top. So this line is going down forever here. It's got an arrow on the end of it. It goes down forever. So that's negative infinity. And then it goes up, and it looks like it's skipping a number here, and it is. It's actually skipping right here on the x-axis. I'm going to draw a little horizontal line there, dotted there. Right there is the y value that it can't be, and that's 0. So the y, the domain is x can't be 0, but the range is the same idea, that this is actually the y value when x was 0 would be that would be the y value that it couldn't be as well. So the range goes from negative infinity up to 0, skips the 0, and then goes on to positive infinity, because this line here goes on up forever there. So we have this imaginary line, that dotted red line there that's going through there. There's also another imaginary dotted line that's on the y-axis here. Those two imaginary lines that I've kind of penciled in there are called asymptotes. One is a vertical asymptote. Asymptote. Vertical asymptote. And it has an equation. It's x equals 0. Okay. That's one of the things we're going to be in charge of finding with these rational functions, are the equations of the vertical asymptotes. And then there's a horizontal asymptote. That's this line that I've drawn that goes sideways there. It's the horizontal asymptote. Horizontal asymptote. Asymptote. The horizontal asymptote is at y equals 0. And we're going to see as we do some of these more complex functions how to find those equations of that. And it's not too bad. It really is tied directly to what we did last week with the simplifying of the rational expressions. It goes back to that. So we're going to go through how to find those and things. So we're taking that original one with the domain and the range, and then these vertical asymptotes, horizontal asymptotes, and then there's another thing that this problem doesn't have one, but there's a thing called an oblique asymptote that can occur, but doesn't always occur. Oblique asymptotes, we used to call them slant asymptotes back in the day. Oblique and slant mean the same thing. They're just an asymptote's imaginary line that looks like a linear equation. It's got y equals mx plus b. This problem doesn't have one. There's only certain times when it does, and we're going to learn some rules during this section about when it does have a oblique asymptote, when doesn't have a horizontal asymptote, and when are there vertical asymptotes, what do they look like, and all that stuff. So we're going to go through finding a lot of this stuff for functions of the rational nature in this section. So first thing we want to do is kind of go back to some things that we talked about with transformations back in Math 100. And transformations are the shifts left, right, up, and down, the stretching, vertical stretching, horizontal stretch, and compression. Remember us talking about those in 100. We're going to describe that in terms of what's happening to the original. Describe the transformation of f of x equals 1 over x. So the original that we're looking at is the most basic rational function, 1 over x. And we're going to look at an equation and hopefully be able to describe what's happening to that based on just looking at the equation. We'll look at the graph as well, but we want to be able to recognize it using the equation. So the first one is going to be this. G of x is equal to 1 over x minus 2. And the minus 2 is with the x. It's not outside of it. It's what we would describe when we're talking about transformations. Remember, things that happened on the inside were horizontal. Things that happened on the outside were vertical movements. So this minus 2 is down here with the x on the inside. So this would be a shift right 2 units. If that were x plus 3, it would be to the left 3 units. So it's always the opposite when it happens on the inside. The horizontal stuff happens on the inside, and it's usually the opposite sign of what's there. So the minus 2 says right 2 units. The plus 2 would say left 2 units if it were on the inside. So here we have a shift to the right 2 units, and that's the only thing that happened to it. If you were to graph that with the calculator, I'm going to leave the original one there, and I'm going to type 1 divided by parentheses x minus 2, and look at what it does. We see it just picks up the blue and then shifts it to the right 2 units. It just picks it up and moves it. That's all it's doing out of that. So we can kind of see that happening there. The goal is to be able to just look at the equation and tell that with what we're doing right here. But you can always graph each one and see, hey, this is what it looks like it's doing. So I know I can get an idea out of that. Let's take one that's maybe h of x is equal to 1 over x plus 5. So the plus 5 is not with the x. It's on the outside. So we know this is a vertical movement. So it's going to shift up 5 units because it's a vertical movement with the plus 5 on the outside. So a plus on the outside is going to be an up vertical movement. A minus on the outside would be a shift down. Remember those little rules about that. If we graph that with the calculator again, and we can go here, and I'm going to type 1 over x and then plus 5. And because I didn't put parentheses, the way the calculator reads that is 1 over x, and then the plus 5 is separate. And if I graph that, we see, hey, the red one is just picking the blue one up and shifting it up 5 units. So that's what we're seeing happening with that. So just trying to remember those rules and connect the dots there. Say k of x is 1 over x plus 3 and then a minus 6. So this one has a couple of things happening to it. It's got a minus 6 on the outside and then a plus 3 that's on the inside is how we would think about that. So with this one has a horizontal and a vertical shift. So it doesn't matter what order you describe those in, but I would say this one shifts left 3 and down 6 units. Left 3 and down 6 units out of that. So this part's the left 3 and this part's the down 6. Inside is horizontal movement, outside is a vertical movement. The ones that seem to give folks a little bit of problem with this is when they start talking about stretching and compressing. And remember that a vertical compression or stretch is going to happen on the outside. And it's harder to recognize outside when it's a multiplication type situation because they'll do this to you. They'll give you a problem and they may say g of x is equal to 4 over x. And that doesn't just really, it's not as apparent as these first three examples are that there's something been done to that problem. Because it's 1 over x and 4 over x don't look much different as far as an equation goes. But here's what's happening. The math that really allows that to happen is actually you're taking 4 times 1 over x. These are the same thing. So 4 over x and 4 times 1 over x are the same problem. And anytime there's a number multiplied on the outside, that is a vertical movement, and because it's a bigger number, it's going to be a vertical stretch. So this is a vertical stretch. If it were a small fraction, like 1/4, 1/3, 7 over 8, anything less than 1, then it would be a vertical compression that if they put that in the numerator. And sometimes that's hard to see. They don't get too tricky with that. We'll do one more of those. Let's say we had something like g of x is equal to 1 over 8x, something like similar to that. There we got that 1 over 8. What you've got to understand is that is the same thing as multiplying by 8 on the inside. So it's 8 times x on the inside of that thing. So that would be a horizontal stretch. But what's tricky about it is the fact that you could actually think about this problem as being that, which is also a vertical compression. And that, like I said, they don't get too tricky with this. And this is not the meat of this particular section. We'll get to that in a second. But it's just reviewing those transformation ideas. The thing about it is no matter what you call that, the graph looks exactly the same. That a horizontal stretch, when you stretch something out, remember we talked about, I don't know if you remember me talking about the silly putty, and you stretch out the picture horizontally, it looks the same as if you compress it vertically. They look the same as far as the picture goes. The equation here happens to look the same. So when you start adding that rational idea, fractions are complicated. And so here's an idea of one that's, the idea is complicated because, hey, a horizontal stretch with a fraction the equation looks exactly the same as a vertical compression. When we didn't have the fraction involved, we could tell the difference because the number wasn't, it was easy to see that there's a fraction there, not a large number. So that's where that can kind of get muddied out of that. And if one of those comes up on your lab, I know one doesn't come up like that on your quizzes, and I've never seen one like that on the final. In 5-6 years of teaching this, I've never seen one like that on the final. So I don't think you'll have to worry about one being that muddy on that. But if your one comes up on the lab, I'm going to count either way. As long as you're describing it correctly and show me what's happening, it's right on the on the lab. So that's not an issue there. Just understand that it could be either, and the graph looks exactly the same. Happens to be that the equation looks the same too. All right, so let's get into the meat of this lesson for this section, and that is those parts to a rational function. So the important parts, and these are the things we're going to have to find for rational expressions. Important parts of rational functions. Okay. So we're gonna find the domain. That's the first thing. We'll find that every time. It's a function. We always find the domain of the function. And remember, if it's a rational function, to find the domain, all we're going to do is set the denominator denominator equal to 0. And solve. And that helps us find the domain of that. So since we're dealing with fractions, that's how we're going to do that. And then the next thing that we'll find next thing that we'll do is we'll simplify, and this is where it relates back to what we did Thursday. Simplify the rational expression, which is exactly what we did on Thursday. That was the last thing that we had done, was simplifying that rational expression. After we've simplified, then notice that we find the domain first, then we simplify. When we talked about that a little bit Thursday, that you could possibly lose some things if you simplify before you find the domain. So we've got to find the domain first, then we're going to simplify the rational expression. Remember, we did that with factoring. Sometimes they'll simplify, sometimes they won't, and that's okay if they don't. But if they do simplify, we need to be able to do that. And then once we've simplified it, that's when we can find those vertical asymptotes. And the vertical asymptotes are those imaginary dotted lines that go straight up and down. And we'll see as we do some examples here what the graph looks like when there is one of those. And the way that happens is you look at what's left in the denominator after you've simplified. If nothing's simplified out, then the denominator that you got when you found the domain, those are going to be your vertical asymptotes too. Okay. Sometimes you will cut out a few of them by simplifying, but it's going to be coming from the denominator. So we're going to look to the denominator to get those. So it's from the denominator of the simplified expression. Okay, that's where we're going to get those vertical asymptotes. And then we get into those horizontal and oblique asymptotes will be the next thing that we're going to find here. So horizontal asymptotes. And there's a couple of rules that apply here with horizontal asymptotes and when they exist for a rational function. Okay, horizontal asymptotes with a rational function. So let's say we have a rational function f of x. When it's a rational function, you have two polynomials, one on top, one on the bottom. We'll call it P of X and Q of X, okay? So when I refer to the top, I'm going to talk about P of X. If I'm referring to the bottom, I'm talking about Q of X, okay? And with polynomials, you had a thing that was called degree, and it came from the highest exponent on the polynomial on the variable, okay? So here's how the rule works. One rule of them, for a horizontal asymptote to exist, it says if the degree of P of X, the top, is less than the degree of Q of X, the bottom. If the degree of the top is less than the degree of the bottom, example of that would be something like x squared on top, x cubed on the bottom. That's an example of that, okay? So like a plain x on the top, x to the fifth power on the bottom. Doesn't matter how much less it is, it just makes the top is smaller than the bottom. That's the key to that, okay? So that's the if. If that's what's happening, if the degree of the top is less than the degree of the bottom, then the horizontal asymptote is y equals 0. Okay. If the degree of the top is less than the degree of the bottom, top is smaller than the bottom, it's automatically y equals 0. You don't have to calculate anything. You just look at that and see that that's happening. And it's automatically y equals 0. That's how that rule works. Okay. We're going to see some examples of that in just a little bit. I'm not going to leave you hanging and just say, follow the rules. That doesn't teach you anything. All right, so there's one more rule for horizontal asymptotes, and that's that if the degree or if the degrees of P of X, the top, and Q of X, the bottom, are equal. If they're equal, then the horizontal asymptote is y equals A over B, where A and B are the leading coefficients. This rule is a little tough to visualize. The other one is pretty straightforward. You don't have to calculate anything. With this one, you've got to have something to kind of go by. An example of that might be something where you have maybe 3x squared minus 7 over 4x squared plus 5x minus 9, something like that. Here, the degree of the numerator is 2. The degree of the denominator is 2. They are equal to each other. So this one, because of that, we know that the horizontal asymptote is going to be at y equals 3 over 4. The leading coefficients, 3 and 4. That's A, that's B. And there is your horizontal asymptote. It's going to be that ratio of the leading coefficients out of that. That only happens if the degrees are the same. If the degrees are different, then it can't be that. Okay? So we've got to recognize what's going on there. So horizontal asymptotes, they have two scenarios where they can happen. If the degree of the top is smaller than the degree of the bottom, there's a horizontal asymptote at y equals 0. If the degrees are equal, there's a horizontal asymptote at the ratio of the leading coefficients. That's the only two ways that you can have a horizontal asymptote. No way you can have one if things are different than that. Okay. Now, that brings us to the next rule, which is about oblique asymptotes. Okay. I numbered that. So let's call this number 5. oblique asymptotes. Oblique asymptotes, there's only one rule that can exist for them to be in the problem. Then, again, if you've got this rational function, P of x over Q of x, you got a polynomial on top, polynomial on the bottom. If the degree of P of x is 1 more than the degree of Q of x. Okay? It has to be 1 more than. Can't be 2 more than, can't be 5 more than. It has to be 1 more than, only 1 more than. So it's got to be like x cubed over x squared, x to the 4th over x to the 3rd, x to the 26th over x to the 25th. It has to only be one difference, okay? On the top has to be 1 more than the bottom. If that's what's happening, that's where, remember I told you when we did that long division of polynomials, it was going to come back up. This is where it comes back up, okay? So long division of polynomials is what we got to do. Then the oblique asymptote is found using long division. We'll get to an example here in a little bit where we'll actually do all that long division with that. All right, so horizontals occur, degrees are the same, or the top is smaller than the bottom. Obliques occur if the degree of the top is 1 more than the bottom. So what that tells us is this special piece of information is horizontal and oblique asymptotes never, capital never, underline never, happen at the same time. Never occur together. Okay. Oblique and horizontals never, ever occur together. If you've got horizontal asymptotes, you don't even have to do, you don't worry about obliques. If you've got obliques, you don't have to worry about horizontals. You don't always have horizontals. You don't always have obliques. Okay. Vertical asymptotes, usually you're going to have, but you're not always going to have horizontals and obliques. Okay. It has to meet the rules in order for that to happen. Okay. There are some teachers that I've encountered in the past that they just teach you to do the long division every single time, and I think it's easier to remember the rules, and gives you less work to do. Long division is not an easy thing, and it takes a lot of time. So I try to do the rules and remember those and use those to help me with this instead of doing so much long division. Okay. So what we're going to do is we're going to take some rational expressions, some examples, and we're going to find the domain, the vertical asymptotes, the horizontal or obliques, if they have either of those, for the problem. Okay. We're going to find all of those that we can. Okay. So let's do that. So let's take an example. Example F, I think. Yeah, example F. And we're going to state the domain, find the asymptotes, whatever kind there are, and last thing that we're going to do is something it's not too far-fetched, is the intercepts. Okay. State the domain, find the asymptotes and the intercepts. So x and y intercepts, x and y. If it has either of those, it may not have those, depending on the asymptotes and what's going on there. All right, so we're going to use a lot of skills that we already have used in the past to try to help us do this. Okay, so here's our first example. F of x is equal to x plus 1 over 2x squared plus 5x minus 3. All right, so they give us this rational function, and they say state the domain, find those asymptotes, and the intercepts for that. So the first thing that I'm going to do before I try to do anything else is find the domain, because that's going to help me simplify later on. If it will simplify, it may not simplify any, but maybe it does. Okay, so the first thing I'm going to do is find the domain. So to find the domain, since it's a rational function, I'm going to set 2x squared plus 5x minus 3. I'm going to set that equal to 0 automatically. And then I'm going to use factoring to try to solve that. I know it's quadratic, and I could use quadratic formula, but because it's a rational function, my brain should be thinking simplify because it's a fraction. And anytime we're going to simplify a rational expression, we've got to use factoring anyway. So I'm going to use that factoring to help me do this. So that's where all that stuff we did from 100, all that factoring that we did, all that review of factoring we did last week is important for this this stuff. So we're going to try to factor this. So I'm going to do the x method. Multiply 2 times negative 3, negative 6. It's got to add to be 5. So that's going to be 6 times negative 1. And because it doesn't have a 1 in front of the x squared, that means I've got to do it the long way. So I'm going to write it in 2x squared minus 1x plus 6x minus 3. Again, doesn't matter what order you put the 1x and the 6x in there. I put them in that order because I saw the 6 and 3 would have something in common together. It really doesn't matter, though. Okay, and then I'm going to group. First 2, second 2. First 2 have a GCF of x, and leaving 2x minus 1. Second 2 have a GCF of 3. And the factored form would be 2x minus 1 and x plus 3. Okay, and I'm going to set each of those equal to 0 and solve them. Plus 1, divide by 2, get a 1/2. So I get x can't be 1/2. And then I'm going to subtract 3, negative 3. So x can't be negative 3, x can't be 1/2. So my domain is all x's if x does not equal negative 3 or 1/2. If I wrote that in interval notation, that's kind of a long one, but we go from negative infinity to negative 3, parentheses, negative 3 to 1/2, 1/2 to infinity. I'm okay with you just doing set notation because you're going to be doing quite a bit of stuff here. And I believe on your quizzes, that's the way it's going to be. I can't guarantee on the final that they won't have it in interval notation. So if you got it in set notation, be able to convert it to interval notation. But I'm okay on the labs and stuff with you just writing your domain in set notation just because it's shorter. You're going to be doing quite a bit of work on each problem. So it takes a little while. Okay. All right. So now that I've found the domain, that's when I go to simplify the fraction if possible. So what I do is I use the factored form that I had right here. I'm going to use that because I've already done the work of factoring it. If it's going to simplify, it'll simplify using that factor. Does this one cancel anything out? Is there any matching factors on this part up here? X plus 1 doesn't match 2x minus 1. X plus 1 doesn't match x plus 3. So nothing cancels. And that's okay. We look to see if something will, but it doesn't always happen. It's nice when it does, but it doesn't really change anything as far as the problem goes, okay? So that means that once we've done that, we can look at the asymptotes. So we're going to have vertical asymptotes. Because nothing's simplified, our vertical asymptotes are going to be at the numbers that were the things that we took out of our domain. So we're going to have a vertical asymptote at x equals -3 and x equals 1/2. Those are our two vertical asymptotes. Okay. If one of those factors had canceled out, you would only have whatever one was left as your vertical asymptotes. So vertical asymptotes should match up with at least part of your domain. In this case, it's all of it. It's both of them out of the domain because nothing's simplified. Okay. So we get vertical asymptotes. Once we find that domain and simplify, the vertical asymptotes is really an easy thing. So it doesn't take a whole lot of work for those. The next thing to do is to look at the rules for horizontals or obliques. And that's the key here. So we can look at the original problem, we can look at the simplified problem. It doesn't matter which one. The rule is going to be the rule no matter what. Okay? So if I look at the original problem, what's the degree of the top here? What's the exponent on that x? What's the exponent on that x up there? 1. What's the exponent on this x? 2. So the degree of the top is 1, and the degree of the bottom is 2. So the top is smaller than the bottom. If we go back to our rules up here about horizontal asymptotes, if the degree of P of x, the top, is less than the degree of the bottom, Q of x, then the horizontal asymptote automatically is y equals 0. That's what's happening on this problem. So we have a horizontal asymptote at y equals 0. Won't have to do any calculation to get that. It's just based on the degree of the top being less than the degree of the bottom. Top is smaller than the bottom. It's y equals 0. Okay. What's that mean about obliques? Will we have any? No. If there's a horizontal asymptote, there's no way you can have an oblique. If there's an oblique, there's no way you can have a horizontal. Okay, so once you find that you've got a horizontal asymptote, you automatically know that there's no oblique asymptote at all. Okay, so we get one for the other. It's a free trade there. All right. Now the last thing we got to do is get those intercepts. Okay, so intercepts are not hard to find. It's to get the x-intercepts. That's the hardest one. The x-intercepts are where what equals 0. What equals 0 if something is on the x-axis? It's where y equals 0. So all we've got to do is set the equation equal to 0. So if we set x plus 1 over, and I'm going to use the factored form, 2x minus 1, x plus 3. If we set that problem equal to 0, here's what all we have to do. The bottom part goes away. We just have this problem, the numerator equal to 0. If we'll just set the numerator equal to 0, That'll find us our x-intercepts. Okay, and I'm using the simplified version. That's why I went to the factored form there. If it would have simplified, there might have been something else going on there. So here we have x plus 1 is equal to 0. So we're going to solve that by subtracting 1. X equals -1. So we have an intercept at -1, 0. When we graph this, we're going to see it crossing the x-axis at -1. Okay. To get the y-intercept, the ordered pair has a 0 in the x spot. So if I go to the simplified version and I plug in a 0 for x, 0 plus 1 over 2 times 0 minus 1, and then 0 plus 3. I plug in a 0 in the place of x. Everywhere there's an x, I put a 0 there. And I'm just going to work that out. I should get a number back. 0 plus 1 is 1. 2 times 0 for this part, 2 times 0 is 0, minus 1 is -1. 0 plus 3 is 3. So I get 1 over -1 times 3, which would be 1 over -3. So it's -1/3 is my y-intercept. So I'm going to see that thing cross the y-axis at -1/3. So just a little bit past the origin, below it. It should be crossing the x-axis. So when I go to graph this, I'm going to look at the graph and kind of show you what these pieces are, where they're at. So go to y equals. I'm going to clear out these others that I've had. And I'm going to, in parentheses, I'm going to put x plus 1 divided by, and then I'm going to put parentheses. And since nothing's simplified, it's quicker for me to just type in the quadratic 2x squared plus 5x minus 3. I don't have to put quite as many parentheses in there. Here's the thing. Even if it does simplify, if you graph the original and the simplified version, they are exactly the same. Okay? So you can always just graph the original and see some of this stuff happening anyway. Okay? So I'm graphing the original. I put parentheses around the top and parentheses around the bottom. Be careful of that. And then I hit graph. I'm going to copy that so I can draw on it a little bit. All right, so here's the picture that we got. And I'm going to stretch it out so you can see it better. All right. We had vertical asymptotes at 1/2 and -3. That's where our vertical asymptotes were, right there. Okay. -3 and 1/2. If I go to my equation or my graph, right here is -3. Notice what the graph is doing. It's hugging up against that vertical line there. Right here is 1/2. There's that vertical line. There's that vertical asymptote. So it's hugging up against that. And then we had a horizontal asymptote at y equals 0, which is right on the x-axis. Look at what it's doing right here along this edge. It's hugging right up against it. It's hugging right up against that horizontal asymptote. That's what happens. That's how you can see those happening. And then we had intercepts. We had an x-intercept that was, we're at -1. If I look at -1 on the x-axis, right there it is. That's where that's crossing the x-axis at. And it said the y-intercept was at -1/2. Right there. That's where it's crossing the y-axis. We can see all of those things happening with the graph of that rational function. And finding it is all just based on that work that we did there. Not easy, not short. No, this is one of the tougher things that we do, but it is doable as far as that goes. All right, let's look at another one. Let's look at example G. F of x is equal to 4x. We'll do something easier. 4x minus 2 and x plus 1. Something like that. Okay. Again, we're going to find the domain. And then I'm going to abbreviate all our asymptotes. We got vertical asymptotes. We'll do horizontal asymptotes and oblique asymptotes. And so I'm just abbreviating VA for vertical, HA for horizontal, OA for obliques. And then we'll get the intercepts as well. So intercepts. Okay. All right. So domain. First thing we're going to do is set the denominator equal to 0. This one's easy because there's no factoring that has to happen because that's not x squared, it's not x cubed, it's just plain old x. So that's easy. I just subtract 1. X can't be negative 1. So that's our domain. All x's as long as x doesn't equal negative 1. Good to know. If I tried to factor this, I could, the top part will factor a little bit. It's got a GCF of a 2, and I get 2x minus 1 over x plus 1. But it doesn't simplify. So it doesn't really help me to factor the numerator there. I'm going to have it done, but it doesn't help me any because nothing's simplified. So that means my vertical asymptote, because nothing's simplified, is going to match what my domain was. My vertical asymptote is going to be at x equals negative 1. We'll get one in just a minute where something does simplify, and you'll kind of show you what the difference is. Okay. So vertical asymptote at x equals negative 1. And then we got to go to our rules to decide if this thing has a horizontal asymptote or an oblique asymptote, if it has either of those. Okay, so the rules for horizontal are that the degree of the top is smaller than the degree of the bottom, or that they're equal. Okay, so this one, the degree of the top is a 1, the degree of the bottom is a 1. They're equal, right? So that means it's got a horizontal asymptote at the ratio of the leading coefficients. The leading coefficients are 4 and 1. So a horizontal asymptote at y equals 4 over 1, or just y equals 4, 4 over 1. If it's a fraction, reduce it if it will. If it's like 6 over 8, reduce that to 3/4, that idea. Okay, so make sure, same rules as always with fractions. You're always trying to simplify if at all possible. But because we have a horizontal asymptote at y equals 4, because the degrees were equal, then that means we don't have any obliques. Automatic. We got a horizontal, we can't have obliques. Okay. Now, this one's a little smaller problem, so it should make the intercepts a little easier to do. So to get the x-intercepts, again, the trick is take the top, set it equal to 0. 4x minus 2 equals 0. Let's solve it. Add 2. 4x equals 2. Divide by 4. X equals 1/2. So we have an x-intercept at 1/2, 0. And y-intercept, find it, plug a 0 in for x. 4 times 0 minus 2 over 0 plus 1. That would be negative 2 over 1, which is negative 2. We have another intercept at 0, negative 2. We have a y-intercept and an x-intercept. We have a horizontal asymptote and a vertical asymptote. If we look at the graph, again, I'm on parentheses around the top, 4x minus 2, divided by parentheses around the bottom, x plus 1. Hit graph. Picture of that, but I can draw on it. All right, so you see that we have a vertical asymptote at x equals negative 1, which was right here. If I draw a vertical line right there, we can see that hugging up against that. As you look at the graph, you see that happening. And it makes sense that it's there. We also had a a horizontal asymptote at y equals 4. 1, 2, 3, 4. And so if I drew a horizontal line right there at 4, we can see that graph hugging right up against that. That's what the asymptotes do. They kind of guide the graph in which way to go. Okay, that's what their job is. And then we had the intercepts. We had an x-intercept at 1/2 right there, and then we had a y-intercept was at -2. Is that right? Yeah, -2, which is right there. That's where it's at. You see that happening with the graph. So the graph ties to what we're finding using these tools that we have. Takes a little practice, but it's doable. Okay. All right. So let's look at a different one. Let's say we had, what letter are we on here? H. F of x is equal to x squared plus x over x squared minus 1. So here we have fairly simple looking rational function, and we're going to do the same things. We're going to find the domain, asymptotes, vertical, horizontal, or obliques, and then get the intercepts, the x and the y intercepts out of that. So for this one, we're going to start with the domain. I'll set x squared minus 1 equal to 0. And remember that my job is to simplify next. The last example we had didn't simplify. So because that has an x squared on it, that tells me I need to try factoring with this. And x squared minus 1 is a difference of squares. It's x squared minus 1 squared. So that would give us x plus 1, x minus 1 as the factors for that. We set those equal to 0. Solve them. Just the opposite signs. X can't be 1. X can't be -1. And I'm just going to write it. X does not equal plus or minus 1. Shorthand for the domain on that. And then I go and I try to simplify. The numerator will factor with a GCF. What's the GCF of x squared and x? It's x. So there we have a factor that matches. So they cancel each other out. So the simplified version of that is x over x minus 1. Because it's simplified, that changes our vertical asymptotes. That's what simplifying does to it, is it changes the vertical asymptote. Okay, so our vertical asymptotes, VA, are going to be from the simplified version. The only thing left in the denominator is x minus 1. So our vertical asymptote is the only one we have is that x equals positive 1. The x equals -1 was part of the domain, but it's not a vertical asymptote this time because of the cancellation in the simplifying step. That's what happens when you have a factor that cancels out. It changes the vertical asymptote. Now, horizontal asymptote or oblique asymptote. Well, the degree of the top, if we look at the original, it's squared over squared, so they're the same. If we look at the simplified version, first power over first power, so they're still the same. That rule is the same whether you look at the unsimplified version or the simplified version. Okay, so if you have trouble simplifying them, you can still get the horizontal asymptote or oblique asymptote rule done correctly because it's going to be the same. It's not going to change how the degrees interact from simplified to non-simplified. So this one, the degrees are the same. So we know that degrees are the same. There's no way that there's an oblique. It has to be a horizontal, and because they're the same, it's the ratio of the leading coefficients, which are 1 and 1 in this case. Y equals 1 over 1, which is 1. And so we have a horizontal asymptote at 1, a vertical asymptote at x equals 1, and no oblique asymptotes. Now we got to get the intercepts. This one's not hard to get intercepts on because the numerator of the simplified version, we set it equal to 0. What? We're already done. 0, 0. And then the y-intercept, we just plug in a 0 for x. 0 over 0 minus 1 would be 0 over negative 1, which is 0. Hey, that's the same point. We already got that one. So there's only one intercept here. It's at the origin 0, 0. It's an x-intercept and a y-intercept because that's the only point that does both of those. Okay. And again, you could graph that. Clear x over parentheses x minus 1. Let's graph. Show that. Again, we see that vertical asymptote at positive 1, that horizontal asymptote at positive 1, that x-intercept, or that only intercept we found was at the origin, and right there it is in that graph there. We see it crossing right there. So we see all of those things we're finding are happening in the picture. If they're not, then something, either we're not typing it in right or we're not working it out right. Okay, so be careful of that. All right, now let's take one and let's do this. H. G of x is equal to x cubed plus x over change that to an x squared. X squared plus x over x minus 1. Something simple. We'll make it simpler there. This is the first one like this. I don't want to get too deep right yet with the first one like this. All right, so going through the same motions, we're going to get the domain, we're going to get the asymptotes, we're going to get the intercepts out of that. So domain, we'll start with that. Domain would be setting the denominator equal to 0. Because it doesn't have a exponent on the x, that tells us, hey, we don't have to factor. That's nice. That means I just solve it. Just get x by itself by adding 1. So x equals 1. All x's as long as x does not equal positive 1. Pretty easy domain on that one. When I go to work this problem, though, I need to look and see if it will simplify. So the numerator will factor a little bit. I got a common factor of an x there. But it leaves x plus 1, not x minus 1. So it doesn't cancel anything. So we don't see anything canceling here. So if nothing cancels, we know that our vertical asymptote is just going to be take that denominator equal to 0 and solve it again. So we get a vertical asymptote at x equals 1, which is the same as we found with our domain because nothing canceled. Remember, if something cancels, it's going to be part of the domain, but not all of it. Okay. This time, nothing canceled. All right. Now we can do horizontal or oblique. All right. Rules are if the degrees are the same or the top is smaller than the bottom, then there's a horizontal asymptote. Well, what's the degree of the top here? 2. What's the degree of the bottom? 1. So that's a case where the top is bigger than the bottom. So if the top is bigger than the bottom, we No, it does not have a horizontal asymptote. Then we check to see how much bigger is the top than the bottom. If the top is one more than the bottom, then there's an oblique. 2 compared to 1, 2 is one more than 1. So that means we do have an oblique asymptote. So there is an oblique asymptote here. The way we find it is we do long division. So I'm just setting up x minus 1 on the bottom, and then on the inside of the house, you got your x squared plus x. And I'm going to go ahead and put a plus 0 over here on the end because it doesn't have the plain number there like this part out here does. All right, so remember when we did long division, we looked at the front piece and said, okay, I'm looking at this x. How many, what times x will give me x squared? X does. So I distribute that x. X times x is x squared. X times -1 is negative x. And I subtract that whole thing from what's above it. These cancel out. That's what I wanted to happen. X minus negative x is 2x. And then I bring this down. So plus 0. And then I look at this front piece again. What times this x will get me 2x? Positive 2. So I put a plus 2 up there. And I distribute. 2 times x, 2x. 2 times -1 is -2. Subtract all that. The x's cancel. That's what we wanted to happen. 0 minus -2 would be positive 2. This part, that's the remainder. That doesn't matter. Remember that from doing long division before, that's the remainder. The part that matters is this stuff up here. That's the equation for the oblique asymptote. Y equals 1x plus 2. That's our oblique asymptote for this problem. Okay. Oblique asymptotes will always have that form y equals mx plus b, where you're plugging in a slope. You got a slope and a y-intercept. They're always going to be that kind of equation. That's what you're going to find. Okay. Let's look at the graph and we can see that equation or that slant asymptote or oblique asymptote happening. Clear it out. I got x squared plus x divided by parentheses x minus 1. Graph. All right. Because I got an oblique asymptote, I'm going to actually graph it with the calculator and let you see that line. It was x plus 2. Look at that red line that I've graphed through there. That's our oblique asymptote. Look how the graph hugs up against it, just like it did with the horizontal and verticals, right? If I take a snapshot there, pop that down on the page. Oh, it stretches it out so much. So here we have that red line is y equals x plus 2. That's our oblique asymptote. That's what that is. Okay. We also had a vertical asymptote at 1. Right there it is. That's x equals 1. That's our vertical asymptote. That's what that is. And then we hadn't found our intercepts yet, but we're going to. So let's find our intercepts. We'll take the numerator, x squared plus x, set it equal to 0. I remember factoring that a while ago, so that's going to help me because I can factor out an x and it leaves me x plus 1. So I get x equals 0, x plus 1 equals 0. So I'll get 2 x-intercepts there, one at 0, 0, and then one at -1, 0. And we can see that it's crossing the x-axis at 2 places, one right there and one right there. And then my y-intercept would be plugging a 0 in for x. So f of, I think I did g of x. G of 0 would be 0 squared plus 0 over 0 minus 1. That'd be 0 over -1, which is 0. I already have that ordered pair listed, 0, 0. So I have those intercepts, and we see both of those on the graph of that rational function. All right. All right, let's look at another one. One that's a little bit more stuff going on. As we're learning more of this stuff, we got to kind of start stepping it up a little bit more. So we had f of x is equal to 3x squared minus or plus 5x minus 7 over 6x squared minus 150. All right. So again, we're going to find the domain, the asymptotes, vertical, horizontal, or oblique, and then the intercepts of this problem. So that's what we're going to look for here. So domain first. 6x squared minus 150. Set the denominator equal to 0 and factor it if possible. So 6x squared minus 150. I go through my rules of factoring. GCF is first. So what will go into 6 that will also go into 150? I know 2 does. 3 also does. But if 2 and 3 do, then I bet 6 does. So if I just check that real quick, 150 divided by 6. It does. It goes evenly. That's nice. Doesn't always work that way, but it does on this one. We're going to use it. So 6 parentheses x squared minus, and it said it was 25. And then when we're going to solve that, we divide by 6 and it goes away. We get x squared minus 25 is equal to 0. That's a difference of squares. X plus 5, x minus 5. And then we set those equal to 0. And we know what's going to happen with that. It's just going to change the sign. X equals -5, x equals +5. So our domain, all x's as long as x is not plus or minus 5. I use factoring there because I'm going to need it to simplify if I need to simplify. If they just ask you for the domain of the problem, you can use whatever method you want to solve that. If you wanted to use square roots or quadratic formula, you could as well. But I used factoring because I'm going to try to simplify because I'm doing everything on this problem. So I know the bottom part is 6 parentheses x plus 5, x minus 5. I'm going to try to factor the numerator. I don't know if it does or not, but we're going to try it. So I'd use the x method. 3 times -7 is -21, and add to be 5. Well, the only ways to get 21 are 7 and 3 and 21 and 1. So if I did 7 and -3, that's 4 that it adds up to be. So that doesn't factor. So it doesn't simplify. So numerator doesn't change. So that means nothing can cancel out. So that means my vertical asymptotes are going to be the same as what the pieces from my domain. So my vertical asymptotes are going to be x equals 5 and x equals -5. I'm going to have 2 of them, just like I had 2 pieces that were cut out of the domain, the +5 and the -5. Same ones for that one. Okay. Now, look at the rules to see if this one has horizontal or oblique or neither of those. It could have neither of those. Okay, so we go back to the original. That's always the easiest place to get the degrees. The degree of the first one, the top is 2. The degree of the bottom is 2. That's equal. So that means we have what kind of asymptote? Oblique or horizontal? If they're equal, if the degrees are the same. If the degrees are the same, we'll have a horizontal one at the ratio of the leading coefficients. Leading coefficients, 3 and 6. Reduce that to 1/2. Y equals 1/2. Since we have a horizontal one, we can't have an oblique. They do not happen together. All right. Now, let's get our intercepts. X-intercepts, set the top equal to 0. We've already tried to factor it, and it wouldn't factor. How can I solve something that's quadratic, but it won't factor? Quadratic formula. Remember, plugging in that stuff. So -5 plus or minus the square root 5 squared minus 4 times 3 times -7 over 2 times a. I'm going to use calculator to help me a little bit. 5 squared minus 4 times 3 times -7. We'll get 109 underneath the square root. That doesn't simplify. Square root of 109 doesn't simplify. I know 109 is prime. So I know that doesn't simplify any. So we're going to have two x-intercepts at one at -5 plus the square root of 109 over 6, 0. The other one at -5 minus the square root of 109 over 6, 0. That's our x-intercepts. To get our y-intercepts, we're going to just put a 0 in the place of x in the problem. 6 times 0 squared minus 150. Well, all of these things are zeros. They're all gone. So that's -7 over -150, which is just 7 over 150. I don't think that simplifies. I'll check it with the calculator. 7 divided by 150. And then hit math, enter. And no, it doesn't. It came back 7 over 150. So we get a intercept at 0, 7 over 150. So we get some weird intercepts for this one. But life ain't always pretty. That's for sure. Math ain't either. So you could graph that and verify all of those things with the graph out of it very easily. Okay, just graph the original, put parentheses around the top and the bottom, since it didn't simplify. All right. Let's look at look at this one. Page here. I have no idea what letter we're on. J, I guess. That's what I'm going to put anyway. All right, so we have, let's do this one. X squared plus 7x plus 3 over x minus 2. Again, we're going to do the same Same stuff, domain, asymptotes, intercepts. That's what we're going to find here. All right, so x squared minus or plus 7x plus 3 over x minus 2. Let's find the domain. Again, that's setting the denominator equal to 0. Good news is we don't have to do any factoring this time for the denominator. X minus 2 doesn't factor. We just add 2. We know x cannot be 2. So our domain is all x's as long as x doesn't equal 2. And then let's try to factor the numerator. So if we could see if it'll simplify, you multiply by 3 and add to be 7. 3 and 1 is the only way to get 3, or negative 3 and negative 1, which would definitely not add to be 7. Neither of those work. So the top doesn't factor. So it doesn't simplify any. So that means that my vertical asymptotes are exactly the same as my domain was. X equals 2 is the vertical asymptote that exists. Will this one have a horizontal or an oblique asymptote? And why? The oblique, why? What's the degree of the top? It's 1 more than the degree of the bottom. We got a 2 over a 1, right? So this is a 1 power on that x. 2 is 1 more than 1, so that means it has to be an oblique. So on the horizontal asymptote, we just put none. An oblique, the way we find that is we got to do that long division. So we're going to set up x minus 2 on the outside. On the inside, we got x squared plus 7x plus 3. Yeah, plus 3. We're going to do that long division, and it doesn't matter what the remainder is. We're just doing the division to get that y equals mx plus b part for the oblique asymptote. So what times x gives me x squared, x. So distribute x squared minus 2x and subtract. X squareds cancel out. 7 minus negative 2 would be 9x. What times x would give me 9x? Be plus 9. Would be 9x minus 18. Not that it matters. Because once I get this, mine automatically know my oblique asymptote is x plus 9. I don't even have to work out what the remainder is because it doesn't matter. The remainder doesn't matter when you're looking for the oblique asymptotes. You don't even have to work it out. You just got to get y equals mx plus b situation happening. Okay, we have an oblique asymptote at x plus 9, a vertical asymptote at x equals 2, and no horizontal asymptote. The next thing to find are the intercepts. Okay, so intercepts sometimes can be difficult. If we get the x-intercepts, we're setting x squared plus 7x plus 3 equal to 0. And I've already tried to factor it once. It didn't work. So I've got to do quadratic formula again to try to find the x-intercepts. Okay? And that's absolutely fine to do every time to find x-intercepts. But always try to factor to simplify before you go get this far. Okay? So I'm going to set up x equals negative 7 plus or minus 7 squared, 4 times 1 times 3 over 2 times 1. So this one's a little better. Not quite great, but it's I can do those numbers in my head. So that's 49 minus 12, which would be 37. So that won't simplify. I know 37 is a prime number. So I know I've got x-intercepts at negative 7 plus the square root of 37 over 2, 0. And then negative 7 minus the square root of 37. over 2, 0. So those are my x-intercepts. To get my y-intercepts, I'm going to put a 0 in the place of x in the original problem. 0 squared plus 7 times 0 plus 3 over 0 minus 2. Well, that works out a lot better. That's 3 over negative 2. That's my y-intercept then. Is at 0, negative 3 over 2, or negative 1.5 if you wanted to do decimals there. So there are my intercepts for that problem. We're finding intercepts, all those asymptotes out of that. You got to know those rules for vertical and horizontal, or rules for obliques and horizontal asymptotes. That if it doesn't fit one of those rules, then it doesn't have either of those. Okay, so the only time it has horizontals if the degrees are the same or the top is smaller. Only time it has obliques is if the top is one more than the bottom. That's the only time it happens. In your textbook, there's a box that kind of summarizes a lot of this stuff. That's handy to have. I think check the page number in the new version of the book. I think that's what folks that have one. That's what version they've got. Read. 392. Well, that's not what page I have. 350. Yeah, it's not in the new version. The older version had a nice box that kind of just put it all together, but this one doesn't. So. Ah, there it is. Found it. Oh. That's polynomials. Right there. Page 367 in the newer version of the textbook. Page 367, there's a box. It's green in the textbook there about graphing the rational functions and all of those steps out of doing that. So it's a nice little summary of those things that we found. So it just kind of reminds you of everything that we have to do. But it's the things you need to be able to do are the exact things that we've done in the notes here. Practice problems for this particular section, page 373. This is section 3.5. 1 through 105. Just and some of in those subparts there, it just asks for one part. You don't have to do all the parts on all of those, but it gets you good practice out of that. And there's a lab that goes along with this that you'll do as well. So so easy practice there. Get you kind of pieces at a time, and then puts it all together at the end of that. So that'll be the first section that we're doing tonight. Let's take a break. There's a lot to intake there, and we've been at it for about an hour and a half. So let's take a break and come back at 15 till 6, and we'll pick up with the next couple of sections. They're not quite as long as this one was. So let's take a short break.